another ionizer. I do try to avoid making videos about too many similar things in the vicinity of each other, but this one merits special attention because having recently made a video about an ionizer, I thought I'll make a video about this one. I'll try it out first, and it kind of died. I mean, it started off really enthusiastically and it's dead. It's making purring noises, but it's not ionizing anything. Now, when I test an ionizer, I use a cheap emitter like this. I ground one lead, the negative lead is the ground reference, and I connect the other to a metal plate. And here is a traditional ionizer, a super reliable vintage Mountain Breeze ionizer, the type that I recommend because they are just the simplest, most robust design. Now, if I turn this on, you'll see it's detecting a slight ambient charge, not that much, of about 15 millivolts, a negative charge. If I turn this ionizer on by plugging it in, and I've deliberately left it overhang the bench because that is the best way to do it, so I'm going to plug this in and you immediately see the charge on the bench increasing. This isn't necessarily a good thing for electronic components. Oh, that's gone way off scale. Okay, so now I'm going to hold the plate in front of the ionizer, and when I hold it in front of the ionizer, it goes up and it goes up, and as I get closer and closer to the emitter needles, it goes well above 1 volt. That is quite high, isn't it? It's quite good that you can actually do it. It provides a good indication of output. And it is it's a really good indication of how much it's putting into the air in terms of an electrical charge. Now, I'm going to unplug this ionizer and put it out the way since it's proven it's set the standard, if you will. And I'm going to plug in the shitty Chinese one, which did kind of work and is probably going to make a mockery of me now by working, but I'll plug it in. Okie dokie. It's making a noise. I don't know if you'll hear this. I'm going to put it at the edge of the bench like the other one. I'm going to hold the metal plate in front of it and it's showing nothing. Let's turn it down. It's probably the residual charge it's going to pick up. It's not showing anything at all. It's showing like residual charge in the previous ionizer. It's nothing. So this is dead, but it wasn't dead when I first plugged it in. When I plugged it in initially, it made the usual fuzzing noise that ionizers made. A very noticeable draft came out the front of it, which is good. That's the ionic sort of breeze you get. I'll just put these things out of the way. And I placed it on a pile of photo frames shrink wrapped in sort of polyethylene, as I believe you say in America. And when I placed it on it, there was a distinctive fizzing, weird, it was quite unusual, a fizzing, crackling noise from the plastic as I put it on it, which is interesting. But anyway, it's dead. It's all a moot point. It is deceased, and it is already unscrewed because I've had a wee peek inside, and I have to say it's quite nice construction. I don't know if it's still holding a charge. It's not holding a charge. So it's got a section in here it's got a circuit board, and then it's got a section in here potted in resin with the high voltage section, and then a sort of channel, and you can see a slight dribble of the resin has gone down where they've just pressed these carbon fibre emitters, carbon fibre being a great choice of emitter, and they've pressed it into sort of grooves, and then they've flooded the resin to make it sort of resistant to the high voltage, which I fear it may not have been resistant to the high voltage. But the circuitry is odd. I was kind of expecting traditional circuitry, which is very minimalist in these ionizer modules. A long time ago, I took one apart and it was just simply a thyristor and a really clever circuit which charged it in one half of the main cycle and then discharged it through a coil in the other half. And it was a tiny little transformer. And I remember I took a long time, like a very, very long time with heat guns and in my oven and so on to try and crumble away the resin to reverse engineer it. And at the time, this was so long ago that I think it predates YouTube. I had my website, bigclive.com. Mike's Electric Stuff had his website. Mike's Electric Stuff is the name of the website, I think. And I remember at the time, I was so impressed with the circuit, I actually sent a picture of my schematic reverse engineered to Mike, and we had a wee discussion about it. But fast forward to now, and this looks different because there's a 555 timer and lots of circuitry, and it seems like it's using a sledgehammer to crack a nut compared to the old circuitry. I can see two transistor-like components and this 555 timer, and initially, you'd assume that then it's using a power supply, capacitive dropper power supply here, the 555 timer to pulse the coil. But having looked at the circuitry, it's a bit odd. So I'm going to stop, I'm going to pause, and I'm going to reverse engineer this circuitry, and then we can explore it together and see exactly what makes this tick. Well, that took longer than expected, a lot longer than expected. This is nothing that I was expecting, and there's a clue in the listing. Oh dear. It says, description. Why does that look wrong? 8 launch head design effectively improved the unit time of negative ion release. Okay, there's the 8 launch heads, the little carbon fibre emitters. And then it gets a bit weird. It says, intelligent cycle timing circuit design work for 30 to 40 minutes and then shut down for 7 to 15 minutes to ensure that the function of long years of work. Okay. Enclosed shell design, the high voltage side launch head placed in the shutters which effectively prevent the risk of electric shock. What they're talking about there is that the emitters are actually shielded behind this plastic case, and I'm not sure that that's a great thing. To me, the best ionizers have the needles or emitters actually sticking out the front, a bit of protection. You can get a slight fizz off them, but it's not usually, as long as you use a couple of resistors in series, because it's very low current, it's not going to be sort of dangerous. So ABS plastic shell can put in table, in room, car or wall mounted. Suppose you could use in a car with a step-up circuit. Effectively dispel the unpleasant odour, remove smoke, dust, kill harmful bacteria, give you and your families a fresh indoor air. That's the classic claims, the ionizer. Most of them are actually accurate. And power less than 2 watts, which is quite high. And it does turn out the power is about 1 watt. But it depends. It's using a really huge capacitor, the capacitive dropper. Negative ion concentration greater than 800 million cubic centimetre, which is just bullshit random numbers. It's just made up numbers. Application area 10 square metres, presumably. Ozone less than 0.05 parts per million. That's just a random number again. But I took a photo of the circuit board, and the bit about it turning on and off is interesting because that's exactly what the 555 is doing, but it's doing so in the weirdest way. So I took a photo of the top, then I took a photo of the bottom of the circuit board, faded it down using Earthing View just to actually make it a sort of more pastel shade and adjust the contrast a bit, and then I drew in all the components on it after flipping it so that the placement of the components matches, the integrated circuit is here, the integrated circuit is here, big capacitor here, big capacitor here. By flipping the image horizontally, it makes it much easier to transfer. And here is what I discovered, and it's really not what I was expecting. So the circuitry starts, we'll divide it down. There's the ion module, which is a completely separate part of the circuit board. That is basically this side of the circuit board. The rest of the circuit board, the bulk of it, the really power munching stuff, if you will, it's not that much power, but it's still significant, is on the other side, the rest of the circuit board with the 555. So we've got a capacitive dropper here. Starting from these rails here are the mains incoming supply. I've not marked it live or neutral since it is a non-polarized plug. Ideally, this would be neutral and this would be live, but in reality, the way they've connected the colours onto the circuit board is completely different. The circuitry starts with a capacitive dropper with this 470 nanofarad capacitor with a 470k discharge resistor across it. Then there's a 51 ohm resistor, a huge metal film style resistor, which is green, brown, black, which is 5, 1 and 0 as a multiplier, so that's 51 ohms. Very odd value. That's presumably to limit the inrush current. Then there's a Zener diode, which on the basis that the output voltage here was round about 11.2 volts, I'll guess that's a 12 volt Zener diode, and there's going to be a bit of ripple here. There's a single diode coming across, so that on the positive going half of the sine wave, when the Zener diode is clipping, because the other direction it will just actually clip it down to about 0.6 volts, but in the positive direction it will clip it to about 12 volts, goes through this diode, charges this capacitor, which is a power supply smoothing capacitor, 220 microfarad at 16 volts, that's that one down here. There's a Zener, here's a dropper capacitor, and there's that big weird resistor. It then powers the 555 in just the worst possible way imaginable. The circuitry, I mean, that's a reasonable power supply for the 555, but the circuitry is, I'm trying to find where I'm here. Where are the values I wrote down here? This is a 470 microfarad capacitor, right? So quite a long time delay. It's an A-stable configuration for the 555. Very standard timing chip. And then it's got, from the positive, it's got 5.1 megohm, which is huge. And for this resistor here, it's got 2 megohm. And those are huge values. When you're talking about such huge values with the traditional 555 timer, the leakage of the capacitor actually becomes an issue. It can actually affect this, it can make it unstable. And I have to say, I had this plugged in for ages, and according to the information, the data sheet, it says, works for 30 to 40 minutes and then shuts down for 7 to 15 minutes. I left it running for a very long time, long enough to just cause it to completely die, and I never saw that LED go off at all, because the output, well, here's the last remaining component in the 555. It's a little capacitor connected between 5 and the 0 volt rail, which is just for a reset purposes and stability of the chip itself. The output goes via an LED, which is just double function. It's the easiest way to do it. LED, then a resistor, and then it drives a little triac, which turns the ion module on and off, except in this case it didn't, because there's a very good chance that these resistors are trickling the current so slow that the voltage across this capacitor is just never ever going to reach the threshold voltage of the 555, where it will suddenly switch into discharge mode. It's very, very weird that they did that. I can't even work out why they're talking about turning it off. They claim that they're turning it off for the function of long years of work. It's as if it's to save its lifespan. And I wondered, is it because the charge is building up the plastic and it lets it dissipate? But then I remembered there is a certain, shall we say, a quack ionizer, a negative ion generator that you can buy for thousands of pounds. And it's full of just bullshit. Their specification is that it creates ingestible ions. It's got special needles that you have to change, and they're very expensive. It's got a little LED, it tells you when to change needles. That's not this piece of shit. That's the super duper expensive one. And they claim you've got ingestible ions that are super small ions that you can breathe in, and it goes into your bloodstream and it improves your health. That is just utter bollocks. An ionizer puts a negative charge into the air, but one of their features in that was they've got a computer controlling it, a little microcontroller that turns the output on and off, and that's supposed to make it super earth harmonic, negative, super hyper energy health waves. And I wonder if that's the reason that they've got the output with the LED going on and off. And quite frankly, this circuitry here could just have been omitted, because it's just an absolute pointless heap of shit. What actually matters is the ion module. So let's take a look at that. The ion module, which, it's the other bit that's broken down in this. The ion module is a completely different kettle of fish. It's the bit that's potted onto the resin for most of the part. Here is the bit that's potted onto resin. Hold on, I shall get a red Sharpie and squiggle round the bit that is potted under resin that I can't see. I can't see that, so all this is guessing at what's inside, but I kind of know, because I've taken a similar unit apart a long time ago, as previously mentioned, and that's the type of circuitry there was. But this is sweet. This is actually simpler than that other one. This is actually one of those circuits that goes, you're looking at it and think, how does that even work? And then it just goes bing, and you think, that is absolute genius. So here's the mains incoming supply. It's actually switched by a triac from the other bit of shitty circuitry. But let's just say that this is live and this is neutral. And one of the nice things about this is it's easy to adapt. Changing the value of these two resistors would let you adapt it for 120 volt or 240 volt. It's very clever. What actually happens on each half wave, across the sine wave, the polarity affects what happens in each part of the sine wave. So initially, If live's negative and neutral is positive, this capacitor is charged negative to that side, positive to this side, and the thyristor, this resistor here that feeds the gate of a thyristor, because it's negative with respect to the cathode of the thyristor, it keeps it turned off. So the voltage that will go up onto this capacitor depends on the mains frequency and the value of this resistor. They've just chosen the resistor to match, that it will gradually charge that capacitor up to a voltage that they reckoned was ideal. And they've used a 100 nanofarad capacitor. They've not used a sort of peak mains voltage rated capacitor. It's 250 volt. And there's a good chance that because they designed the circuitry in that resistor, it's never ever going to charge above about, say, 200 volts or something. Maybe that's what they're aiming for. Maybe even 100 volts. Then the polarity changes and it goes positive and then negative. And at this point in time, because this capacitor is got the positive charge on this side and the negative charge on this side, effectively the thyristor then, because that is negative and it's seeing the charge across this capacitor here via this coil, which is the primary side of the transformer. When it goes positive and it reaches a specific voltage, the voltage level on this thyristor exceeds the cathode voltage of the thyristor, and it turns it on. And thyristors, when they turn on suddenly. They latch on. It's by design. So as soon as this is triggered, it turns on hard, and this capacitor, the charge that's been put on it, is shunted through this little transformer. And because it's a sharp pulse, the transformer can be very similar to what are used for firing xenon tubes. It can be a little ferrite core with a super bunched up high voltage winding, multiple layer high voltage winding on it, and then a little sleeve, and then just a few turns of the primary round it. And what happens there, this is the primary, and it couples into the secondary, and because the secondary is a lot more turns, it steps the voltage up to a very high voltage. Now, I'm guessing that in here, at the very least, I would expect it to be a diode, maybe a diode capacitor. I'm pretty sure that it may be a couple of stages to create a sort of push-pull effect, a voltage multiplier, just to step it up, and it means the voltage across this transformer doesn't have to be too high. And it'll step the voltage up, and these diodes will effectively point down to the 0 volt rail, which is neutral. And it means that across this capacitor here, you end up with a full voltage, which is going to be a good few thousand volts. Then I'd expect current limiting resistors, and then all the carbon fibre emitters. Maybe they've used a resistor per emitter, but I doubt it. I think that's more for show than anything else. And that is a really clever bit of circuitry. It's very, very simple, but the downside is it does involve semiconductor switching components. It does involve tiny little transformers with very high voltage across capacitors and the diodes, everything in a concentrated space. I reckon that's what may have gone wrong with this, because it seemed to start off so well and then it died. And that's the big advantage of the traditional old school and much more complicated, much more expensive to make capacitive dropper based ionizers. Now let me find a screwdriver. Let's see if I can pop this open just to... Am I going to be able to pop this open? I may be able to pop it open. I may not be able to pop it open. There it goes. In here, that high voltage still exists, but it's right from this end to that end. There's huge separation. There's literally about 3/4 of an inch, half an inch, 3/4 of an inch between each section of that voltage, which is roughly about, say, 12-20 millimeters. And it means that the separation is such that these circuits here are super reliable, unlike what's in these. What's in that potted bit here? I can hear it purring, which suggests it's firing little spikes through, but there's no high voltage. I'm guessing the noise is probably coming from the piezoelectric effect of that capacitor when this thyristor discharges it, making that slight sort of purring noise. But it's failed. It's dead. It's a very nice design, but... in the sense that, you know, one part of it's a very nice design, the 555 bit isn't. But it's all a moot point, because it doesn't work. So I'm not sure what's going on. This is so potted in hard resin and soft plastic that it's going to be quite hard to get that out. Last time when I did unpot the original one, it took ages. It really took a long time. So heating it with the heat gun, then picking it off and destroying components of the process, and then trying to have to work out what they were. Particularly the capacitors copped it big time with the heat gun. The resin casing came off them. But yeah, it's interesting, but it's dead, and that is just the weakness of trying to cram a high voltage in too small an area to save money. But interesting nonetheless. Particularly this bit of circuitry was very, very interesting indeed.